Where were you before you were conceived? Your body is created of so many atoms, and you did not have most of those atoms when you were born, and you probably didn't have most of the atoms that you're born with. But where were these atoms before you were conceived? They were all across the earth. They were flying around in the atmosphere. They were in soils in different lands, probably different countries. The water that makes you, it was probably in different lakes and seas. All of these atoms have now come together in this person that you are. And how did that happen? That seems wrong, that such a thing could happen. It might not seem wrong to you, but if you're a physicist, it does seem wrong. We are going to die. One day, this body will disintegrate into soil. But what about the universe? Will the universe die? Was it born? Why is it that when I exercise and I eat enough protein and I take enough rest, I become stronger and I become bigger, but with everything else that we make, which is inorganic, like this cloth, inorganic in the sense that it's non-living, everything you see here is just going to disintegrate with more and more blows and usage and wear and tear. But why do muscles grow bigger? That is what I want to talk about today in this video, and it might be a little bit surprising what is the commonality between cosmology, life, exercise, and time, the physics of time. All of it is bound by a single law in physics, the second law of thermodynamics. And you somewhat have an idea what it is. We all have an intuitive idea of how time is flowing, what can happen and what cannot happen on its own. For example, if I drop a ball here, oh, I have a ball. That's good. So if it's gonna make a sound that I don't like. But additionally, you see that it didn't rise to the level. And for us, it's obvious that that is what it should happen. It should not rise to your hand, and it certainly should not go even higher. But is it prohibited in physics that this should happen? And interestingly, only statistically, not really. There are laws in physics that inhibit certain things from happening. For example, you cannot exceed the speed of light. Now these are not laws written by a god that we can read and now we know that there is no way to overcome them. But even in the physics that we have written down, there is a law that you will not be able to travel faster than light. But is it the same case with this ball? Is there a law that can say that there could not be what we call a super elastic collision? An elastic collision is when I drop this ball and it reaches my hand again. So there is no loss in energy. The energy that the ball has now, you might think there is no energy, but we call it the potential energy because I use some of my energy that I gain from eating food into lifting this ball to this height, and now it has potential energy. And when I drop it, the energy is lost. Some energy is lost. Some energy is lost in sound, and rest of it goes into heat in the floor. But is there a law that says that this has to happen, that the energy has to be lost? And more certainly, the ball cannot jump up even higher. And the answer is surprising. I mean, you might tell me immediately that second law. Second law is what? Calm down. Second law is not a law that applies to fundamental particles. So if you're talking about two pure particles, not the collection of particles that we see, just two pure particles and they are colliding, you cannot say that they won't collide elastically. But can you say that they can collide super elastically? When you're talking about just fundamental particles, just a single particle or just this set of two particles and the forces between them, if you are talking about a single particle, then there is no such thing as a second law. because you cannot apply this law to a singular particle. Every law in physics is time reversible. So if you play a video clip backwards, ideally you should not know whether it's going forward in time or backward in time. And in certain situations, that is what happens. For example, when you have a video of Earth going around the sun, animation of this event happening, you would know that the Earth is going around the sun or not if it's going in this anti-clockwise direction, but that's only if you know where the north is. If you can't tell where the north is, you cannot tell if this clip is going forward in time or backward in time, because if it's going like this, maybe we are looking at it from down below and that's still the right way, but we thought it was the wrong way because it was going in the clockwise direction. But for things like the ball or the egg breaking on the floor, we can immediately tell that this is the way in which things should happen. And what law is it? Because it's not a law that you can apply to a single particle. Like if you have a bunch of particles, you can somewhat guess what is going to happen to them. And it's not just particles. That's the interesting part. Second law applies in general to collections. It's a law about tendencies. So for example, there's a garden down here, and in the garden there are of course leaves that fall out of trees, dried leaves, yellow leaves, all this stuff, and it has to be raked. Now if you have a rake and you rake all the leaves and collect them in a bunch, as a bunch in the corner, and then you leave, what do you think would happen a little bit later, maybe 2 days later or a month later when you show up? Most of you would predict that the leaves would have scattered by then, not just on the ground but all over the place. And that is something that we understand intuitively. If you left the garden to its own like that, with all the leaves scattered around, is there a law that prohibits that they wouldn't just, with the wind and everything, wouldn't just compile into a heap in the corner? And the answer is no. There is nothing that prevents it. There is no law that says that you can't reduce the disorder in a system. And to explain this, why it never happens, people came up with an explanation with probabilities. It's extremely improbable. It's not impossible, it's just extremely improbable. And I'm talking about leaves, but I'll give you a more classic example. And if you might have started thinking, wait, I already know this physics, the second law of thermodynamics, etc., but you probably do not know the paradox it causes. It does not get talked about. And you probably have heard about Maxwell's demon, which is a limitation or a seeming violation of this law. And we are going to talk about it later in this video. First, let me shed a little bit more light on what the second law of thermodynamics is. I have drawn this to maybe capture your attention. And some of you who have been paying attention might have figured out what this is. We get the energy from the sun, and plants, using soil and air, they create all of these complex structures. The air comes from all over the globe, and some of the parts of our body, some atoms even come from outer space. And then the animals eat the plants, we eat the plants, and then some humans also eat animals, etc. And you build this body. And then humans make all these commodities like cities and smartphones and clothes, etc. Humans die. Humans also take from the soil, but here we obtain very little, like minerals, etc., directly from the soil, and we do not get anything from the sun directly. You might say vitamin D, but vitamin D does not store energy really. Okay, so and humans, using the soil, etc., they make the commodities. Now what happens to the commodities is that they break down and into soil and garbage, and eventually just, well, completely unusable. But then this interesting thing happens, and this is something that is being explained by a couple of theories by physicists, and we'll talk about how there's a new theory that can explain it, but all of the theories have problems. Some of them are far-fetched, some of them are scary to believe in, and things like that. And you will start seeing that second law is not the complete picture. Even though there is a famous quote in physics by a famous physicist, he said that if you have any theory that negates certain physical law, I might support you. But if you're working on a theory that goes against the second law of thermodynamics, I'm sorry, but I have nothing but news for disappointment about you. So we are a little bit scared when we are talking about the second law of thermodynamics. So this is very easily explained by thermodynamics, second law of thermodynamics, that complex things break down into less complex things. It's harder for something to be ordered. Disorder, getting disordered is what all of us are trying to do. And now I'm going to rub this off because we want to talk about what the second law is, because there is a lot of misconception about it. And first it would help if I clarify what the law is. Now, I'm not going to talk about the Carnot engine and everything because it's always confused me, and it's just difficult to understand all those diagrams. Recently, I saw a video of a man being celebrated for creating a machine that creates higher energy output than the fuel that you put in. And people were saying that, oh, that just violates the first law of thermodynamics. So forget the second law. Second law says that the fuel that you put in the machine, you're not going to get all the energy that the fuel contains. Some energy will be lost, except you're heating, if you're heating water. So people said, no, but this even violates the first law of thermodynamics, which is that energy cannot be created or destroyed. Now you're creating energy, and I was there to correct them. It's not necessarily wrong to think that you can get more energy than the input. It violates the second law of thermodynamics, which is an observation. It's not a strict law on the particles. Now most likely he made some calculation error because he was talking about a simulation and not even a real machine. So the output that he's getting is probably due to a numerical error. I'm not saying that he has made that machine or even conceived of it mathematically. I'm not saying that any of what I'm going to discuss is going to allow you to make such a machine, unless human body is such a machine. But let me not digress there yet, but keep watching. So yeah, the basic principle is that if you have a hot cube, and now we're talking about thermodynamics, so it shouldn't be surprising that I'm talking about temperature differences and dynamics or movement of temperature. So you have a hot cube of iron, let's say, and you have a cold cube. Maybe there's only a slight difference between these cubes. What would happen, do you think, when I touch them together? So if this is at 350 Kelvin and this is at 300 Kelvin, so room temperature, and this is 50 degrees warmer, so it would hurt a little if you touch it. Now if you touch them together, you can guess, because you have been living in this world where time flows this way, that the energy would flow like this. Now energy would flow, okay, yes. So basically what 350 Kelvin means is that the particles inside this cube are extremely energetic, not extremely, but more energetic than the 300 Kelvin. And this is not zero, by the way. Even if we had something at ice temperature like 0 degrees Celsius, it still has 273 Kelvin temperature, so it still has a lot of energy. 0 Kelvin is when none of the atoms are moving at all, even slightly. And that's it's not a possible temperature to achieve. So anyway, so you can tell that this energy is going to move, but why? Is it possible that the hot cube gets even hotter when you touch it with the colder cube. It sucks the energy. Okay, it's gonna use the red marker only because it's sucking in the energy, and now this one becomes hotter and hotter and this one becomes colder and colder. And you would think, of course not, of course that's ridiculous. But there's a very important question that you're missing. You are right, it would not happen, but it has already happened. How did this cube become hotter than this cube in the first place when we started the thought experiment? I'll illustrate that point more with another thought experiment. I'll go back to the egg for now. The egg breaks on the ground and it disintegrates into small pieces, and over time it turns into soil and all sorts of stuff. The water just goes away, and if you played a clip backwards, that the soil constructed an egg here suddenly and then pushed it and got it here on the table where it dropped from, you would say that's ridiculous, that can't happen. But when you started this thought experiment, you already had an egg. You already had an egg. So how did the egg come to be in the first place? Here there is life involved and here there is life involved because you burned it, and you burned it using coal, etc. And this is where the life part comes into picture. When we are talking about the classic example with thermodynamics, I'm a little invisible right now, but bear with me. You have a box like this. And the box contains like a lot of particles in one segment of the box and fewer particles in the other segment of the box. Usually the example goes, it's not the number of particles, but the particles in one part of the box are faster and the particles in the second box are slower. So when you open a box here, what you would see is that the faster, eventually it would become equalized. It wouldn't happen that, okay, so it's not that all of them have the same speed and all of them have the same speed here and there is a difference in speed. What happens here is some of them have larger speed than the others, but there is a distribution. So would it happen that the faster particles here would just move into this box here, and now all of these have extreme speeds and all of these have very small speeds or are almost stationary, and these people would just like keep dancing here? And you can do the calculation, and that is what we did in physics courses. The probability is like 0 for all practical purposes. Of course, you're talking about a gas with like trillion particles. So of course it's unimaginable to think, and this is a classic example, but you could also think about there are very few particles here and a lot of particles here. Now would it ever happen that the fewer particles move into the bigger box? Now the first question is there a physical law that prevents it? You might say, oh, pressure. No, pressure is an aggregate law. If you're talking about a singular particle, does it have any mandate? Oh no. It doesn't even know about the other particles. That is an assumption in the gas theory, that they only know about each other when they bump against another particle. Otherwise they have no idea, they don't influence each other. So it doesn't know that it shouldn't move to the next compartment or it should move to the next compartment. It has no idea, it is just moving according to its will. So for a singular particle, time does not exist. If it goes this way or if it goes this way, both are allowed. Of course, these directions are interchangeable, but time's dimension is not interchangeable, and time only comes into picture when you have a bunch of particles and they do something together. And that is something interesting. It's the tendency. Tendency is not something that is defined in physics. Tendency is not like a force, and the particles have a tendency to spread out, to disintegrate. And yes, you could do the calculations and you would find out that it would sort of tend to equalize, and that's sort of a law of physics. But then again, you are not asking the right you are asking the right question, you're solving it, but then there's a huge question that is being missed. How did the box get created this way? Your initial condition is weird. It by your own logic, you say that, so what do we say? We say that if there are two cubes which are at the same temperature, let us say 300 Kelvin, it would never ever happen that suddenly all the energetic particles here move here. Of course, this is solid, so they can't move, but they all like in waves start like sending their energy through like vibrations in a very particular manner, and all of these start to not take that vibration as kinetic energy but immediately start redistributing and in random ways, so it's heat and not, you know, kinetic energy. If all the particles moved in the same direction, it would either be like contracting, expanding, or moving, but if it's like random, then that's what temperature is. So this would never happen, this would not lead to this. And yes, that is true, but how did you start with this? You say that this would never happen, but you're starting with an impossible initial condition which is impossible in. So of course you would say, oh, I heated it up. But that makes things very complicated. When there's a human in the picture, humans are not put in equations very easily. And this is not my research, by the way. I read a very interesting book. Oh, it's over there. I'm not going to fetch it right now. It's called The Animate and the Inanimate by William James Sidis. It's a very interesting book and you should read it. It really challenged all of my opinions about the second. I mean, I always had this question here and I couldn't find a satisfying answer for it. And that book really talks about it. And it gives a theory called the reversibility theory. And we're not going to talk about the reversibility theory. We're only going to talk about the second law of thermodynamics in this class lecture. But you could ask me for the theory in the comments and I'll make another video for it. Now this is the paradox of the second law of thermodynamics, and I'll illustrate this further if you're not convinced that the paradox exists. The primary part of the paradox is we have to come up with a law that is irreversible in physics, only using the laws of physics, the laws of dynamics and kinematics that are completely reversible. So we are forced to derive a reversible law from irreversible ones, and that's not possible. And we don't know at what point, like a single particle doesn't know what it should do. A bunch of particles suddenly know what laws they should follow because they have a tendency together, and that has, I don't know how lucidly this idea of a tendency has been put into mathematics, but we have done great deal of mathematics. First is the mathematics of deriving the probability, and then you can see it as a proof, and it's correct that the reverse doesn't happen spontaneously on its own in life, in the universe, in the physical world. But the other part is we always start with, while giving these examples, we always start with systems with low entropy and we show that they go into high entropy. Don't worry about what entropy really means, but you can see that here we started with energy differences and one had more energy and than the other. Now note a very important thing here. Both of these cubes have energy. One has this much and the other has, okay, it's not that great of a difference. Now here I'm loosely using temperature as the like proportional to energy, but it's not so straightforward. Okay, but basically this is the energy difference between these two cubes, and second law of thermodynamics says that you would be able to use only a fraction of that. So let us say you could only use p percentage of that, where p is less than 100. So even if there is, let us say, 10 kilojoules energy in the temperature differences, you would not be able to get that 10 kilojoules out. You would always get less than it. So whenever you are running a machine and you're putting in some fuel in it and then you're getting some mechanical work done, like driving a car for example, you're always going to lose energy. So you're going to lose energy in form of heat. That's second law of thermodynamics. You drive a car, it gets warm. All of the fuel from the energy from the petrol doesn't go into the speed of the wheel. That's just one example, but we need that for lots of processes. in physics. Like for example, this air conditioner here, it makes the room colder, yes, but it makes the outside even warmer, uh, because it's not just that it sucks in the energy from the room and it just leaves it outside. In the process of doing things, it generates, and the electricity that it actually uses, it creates more heat in the process. So using an air conditioner, it is off. I never use it. I'm a very environmentally conscious person. It creates more heat because there is no other way. Yes, so there is no way to access this energy, which is called the reserve energy. This is called the available energy, and this is the reverse energy. So very simply put, you don't have to worry about the entropy. Very simply put, the second law of thermodynamics states that the total amount of available energy in the universe is decreasing, because with everything that happens on its own spontaneously, you lose energy into heat, and once it goes into heat, it's not possible to take it back unless there is an energy difference. But eventually all of it keeps running down lower and lower and lower and lower into unusable energy, and the most unusable form of energy is radiation, radio waves. Like the radiation that we use, it's very hard to use, and that is why, okay, there was a diagram here. We can't use the solar radiation as energy. It's very hard to use. The plants have figured it out, but yes, the radiation is the least usable energy. So now this question is, if you are making a general law like that, notice how I had drawn a cycle, but nothing I have said about the second law of thermodynamics, that the available energy keeps running down, even indicates that there is a cycle. This is a one street process. So what does that mean? What does it mean that all the available energy is running down? And if this law is universally both in space and time valid, then that should mean that the energy keep running down, and then finally there should be no available energy. So that means everything would be dead. There would only be heat in the universe and nothing else. And this is what is called the heat death of the universe, and it's not new. It's not invented after black holes. Because okay, you might have heard that black holes evaporate and then eventually in the universe, I mean, first what would happen is everything would get sucked into black holes, and then very slowly black holes will leak out radiation, and finally there would be just radiation. All the mass of the black holes would be converted into radiation. Radiation is just non-matter energy. It's just pure energy. It's electromagnetic waves, it's electromagnetic disturbances. You can't hold it. It doesn't have a mass. And finally, that is what would happen at the end of the universe. When the universe dies, it's the heat death of the universe. And that is the current prediction. But what people don't talk about, I have never heard anyone talk about, is what happens when you run the law backwards. What must have been in the past, in the same amount of like infinitely long time ago. What is the opposite of a heat death? Cold birth. There must have been a cold birth. And what does, I mean, I'm not just finding antonyms for heat and death. Let us run the law backwards and see what we find. If the available energy is running down into unavailable energy, which is heat, the temperature, it should go into the reverse when you run time backwards, and it would seem wrong that you're taking out reserve energy or heat energy and putting it into kinetic energy, and that would be correct to feel that it is wrong because we are running time backwards, and we keep running time backward and backward and backward, and at one point we should find out that there was no reserve energy, there was no heat. Every single body in the universe, no idea what it used to be back then, was at absolute zero. And then okay, how did it begin then? They were all at absolute zero, and all the energy that they had was kinetic, because we have energy and we assume that energy cannot be created or destroyed. So what that really means is they must have had the energy in kinetic form. So they were flying very fast back then. I mean, the bodies, whatever that has come down to this here. So in the universe, extremely long time ago, all of the particles, all the bodies were at absolute zero, and they were flying in a way that they were not colliding. So this can be done in two ways. Either they were expanding radially outward and then not colliding anything because they are all moving in directions where they would not have any collisions, or they were moving together. Now they would have to collide with something else, otherwise how did this everything begin? If they're moving in a like a lattice floating, none of like all of their relative velocities being zero, then nothing would happen. It's as if they are just sitting and nothing is happening. But then you collide them with another universe, and this might sound ridiculous, but this is not from my mind. These were used to be popular theories before the modern cosmology with relativity and everything came about. These were called semi-universes or hemi-universes, I'm not sure, but they were half universes, each of them at an extremely cold temperature and extremely high speeds, coming and colliding and creating all of this. But then you are faced with another problem. Gravity exists. So you're thinking about particles, but they should be like, how did gravity not pull them inside? And by the way, when you run time backwards, gravity still works in the right direction. This is something that is interesting to think about. So if I drop this ball, it would accelerate downwards, and you would conclude that acceleration is downwards, gravity is pointing downwards. If I reverse the clip, the ball would reach my hands and I grab it. Instead of dropping it, it would do this. And you would say that yes, the velocity here was in the positive, let us call it y direction, and then here it's in negative y direction. So the velocity is, the sign of the velocity has been flipped, but the gravity, the sign of the force acting on the particle, has not been flipped, because when I drop, the speed is increasing in this direction, so acceleration is in this direction. But when you reverse it, here the speed is more and here it's less, and here it's zero. So the ball has decelerated. That means that speed has gone down, so acceleration is still pointing downwards. So when you run the simulation of these semi-universes with all their particles backwards, then you could also use gravity in the normal intuition that they should have been balls. So at some point, the balls exploded in this weird fashion, created a lattice where there was no interaction and everything was at absolute zero, and then it collided and then it created all of this. And yes, it does sound ridiculous, but that is the logical consequence of the second law of thermodynamics. You could come up with a little different variations of this theory. Maybe it was like radially outward, but you have to go back to some sort of an explosion or something like that, and it's not a steady state. What we saw here with the cycle here, that's a cyclical state, and we are used to thinking about things in the life cycle and all sorts of cycles in a very stable way. Nothing changes, etc. At the same time, we know that time is moving forward. We know that we used to be hunter gatherers and now we are living in amazing, I mean, not everyone is living an amazing life, and people are still living like hunter gatherers. But at least we know that the buildings and the smartphones, there is some linear growth happening in time. One day we will create a world for those who have nothing. Those who have nothing will become everything. So we have an idea of time moving forward. We are born and we die. There is a cycle, of course. Another person lives and dies. From my rotting body, flowers shall grow, and I am in them, and that's eternity. Edward Munch. But at the large scale, we would be happier if the universe was a steady state. So that means that it had neither an end or a beginning. Unfortunately, I mean, you can't really say unfortunately, because in physics you don't get to choose what theory comes out. Sometimes it's very elegant, sometimes it's a mess. You just have to accept what the universe is. It may be completely random even. But if it comes to ridiculous conclusions, then it should give us a pause. And the thing is, every physical theory of phenomena that we don't really understand relies, I mean, each theory has its own stretched conclusions or assumptions, shaky assumptions, and you need to pick your own poison. For example, with dark matter, is it dark matter or is it MOND? But don't worry, if you don't understand any of this. I sidetracked a little bit. Let us get back to the problem of what the second law of thermodynamics explains and what it doesn't explain. It tells us and it does the mathematics. I mean, the mathematics is not contained in the law, but we have an idea why things happen a certain way. For example, if this room is hot and if outside is cold, and if I open the window, I can expect that the hotter and faster and perhaps even more number of molecules should rush out, and not the other way around. The hotter molecules outside would not come inside and make the room even hotter. And it is correct. When you do the math, it works out. But then the question remains why the room was hotter in the first place. That was the first paradox. I mean, the first paradox was that we have to derive a law of physics which is irreversible from reversible laws. The second is starting with initial conditions which we ourselves believe would never come to place. And the spontaneity here is the problem. We think, okay, we can create such conditions, we can heat the box, we can create the egg. I mean, we are also chickens, like I'm saying animals. But it can't happen on its own in a dead world. But then we are missing out a very important piece. Are we to say that we are not physical objects? We are different? Are we not made of the same matter? Is there a magical life force here which makes the muscles grow and a child grows bigger? The child, well, a body, all these atoms from all over the world get pulled into this amazingly functioning body. But even if you think about something as little as the fact that when you eat protein, it gets broken down into amino acids which go into the blood and which goes into the muscle, and the muscle takes the amino acids and puts them into very, I mean, the muscle doesn't do it. Does it matter? The muscle does do it into very complicated, extremely large protein, and it is used to make the body. It should sound ridiculous to say that smaller things spontaneously come together to build very complex things and not just random complex things. And this is the question that has bothered people. I don't like you calling anyone Lord, so just imagine who I'm talking about when I say Kelvin. Kelvin said that Kelvin talked about this. Schrödinger, in his essay What is Life, he talks about it in the section about entropy, and he calls it negentropy. And he says that I feel ridiculous, I feel scared to say something like this, negative entropy. What he means is that this question is very fundamental. Why is my body not breaking down? When I die, it immediately starts disintegrating and just turning into soil. So why is my body not breaking down? And I used to explain all of this, and some of you who watch my channel, I had uploaded a pretty nutty video. It had some interesting points. It was nutty, it was wrong, about how, I won't go into the video right now, but I had explained this through the idea of surplus theft. So what I meant to say is the proteins do break down, and the only thing that they do is break down. We construct protein at a very slow rate, and we eat plants and the animals who have spent a long time creating that protein, and that is what we take. So in my idea back then was that protein just takes time to be made, and we just steal that time from them. And this is in parallel to the labor theory of value, where value of each things is roughly, I mean, okay, the value is of this piece or this piece, the money I mean, is proportional to the amount of labor that has been done by them, and the rough unit that is used to measure labor is hours. So the longer it takes to make something, the more expensive it costs. In general, on average, and you're talking about, let me not go into economics right now. So that this was something similar, and that is how I was explaining it, that people, I mean, we take this protein from animals, and that is why we don't disintegrate, because we always keep ourselves in a surplus of protein. We always have more than what we need, and whenever it breaks down, we replace it. But it has a lot of problems, and let me not go into this problems with this theory. Let me go back to Schrödinger's. Even he was bothered by the fact that human bodies don't break down like any other object, despite the complexity and how delicate all these small molecules are. And he explained it. He said when we eat the animals, when we eat the plants, we take negentropy, or rather we take order from them. Negentropy is just so I'll just write it down, you don't need to worry about what this is. So entropy is like absolute, not just the change in entropy, is defined as the don't worry about what that means. This is let me not, and I think I wrote something. I mean, I missed a constant here, the Boltzmann constant, and I'm just messing up on this. The point is, you just multiply the formula with a minus sign. That is negentropy, and that is basically order. So human beings eat order, and that's how they stay alive. But very crucial piece of this missing information was provided by William James Sidis in his book, and his theory, I'll come to it in a minute, about how this happens, why life doesn't just disintegrate, and what can we have if we change a little bit, if we generalize the second law of thermodynamics, not as a, you know, from A to B straight line law, but something more bidirectional. And it might be a little bit difficult to think what I'm talking about when you're talking about something like this, time like this, but it does well in certain aspects, explaining things that modern theories cannot explain. So of course, now it's been a question, and Veritasium has made a video about it, but I did not understand it, or I think it was not sufficient, or not good enough in the sense of how all this organic matter comes to be. And I think in the end he boiled it down to the radiation that the earth receives and the radiation that the earth emits. The energy is the same, because since we are not increasing our temperature, barring global warming, we are not increasing our temperature, because otherwise we would increase the temperature if you're not emitting the same amount of energy out as we receive as a whole, as a whole earth. If earth received more energy than it emitted, then it would get warmer. So we do emit out all that energy in form of radiation, but then all of these things happen here. The trees grow, we create all of this. So the energy, it leaves, but then it leaves us with lesser entropy, and he explained that that entropy is still increasing because the radiation that we emit is of a different wavelength, and that has more entropy. I think that is what I remember from the video. If I was wrong, I'm sorry, Derek, you're not even watching this video. But is that all? I mean, okay, so there are two theories. Okay, the theory that physicists talk about, if you ask a physicist, if you ask a biophysicist, how did the life come about? It doesn't make sense that something can just, you know, all these atoms can come together in more and more complex phenomena, and they are absolutists in this regard. I'm not demeaning them, maybe this theory is correct, who knows. We're talking about hypothesis here. But if you have to go along the second law of thermodynamics, then you have to say that it is natural. And this is a famous quote, that if you shine enough light on the soil, you are bound to have a plant. That follows the second law of thermodynamics. Of course, if you think that second law of thermodynamics is never violated, then of course that is the logical conclusion you should come to. But then a lot of physicists are bothered by the implications and the problems about life and second law of thermodynamics. So even Schrodinger talked about negentropy. The one thing that I said that I would discuss, I haven't, is there is another seeming violation in second law of thermodynamics. Imagine that there is again a box, and there are particles in one side of the box, and then there are particles in the other side of the box, but then there are more particles in one side and then the other side, and there is a door. But this time there is a flap on the door, and here sits a devil. Not the devil, it's called a demon. It's not even called a demon, it's the daemon, the weird, I think it's the, and this is Maxwell's daemon. What the daemon does is, every time a particle is about to enter from the less populated region into the more populated region, it shuts the trap. Sorry, it opens the trap. So this particle would go here and then it closes it, so none of the particles can escape. So it never opens the gate when there is a particle who might leave. It only opens the particle when there is, by opening only a particle from here goes here. So eventually, by opening and shutting this, all of these particles would end up in one box, and that should not happen according to the second law of thermodynamics. This is ridiculous. It should only be one way. And if you ask this question to physicists, they will tell you that information is entropy. And again, it seems like I'm talking about I don't approve of the physics. That's not the case. But I'm just telling you what is the standard explanation for this problem currently. That they say that the mind of the daemon, he is storing information, he is doing something. So the mind has changed now. So eventually the entropy of the system has still increased because the content of the information in this brain has increased. And again in all the paradoxes and the seeming violations, we come up with intelligent biological agents. We are the ones who actually do create differences in energy. We heat up water, we drive cars, and we do all sorts of things which change energies between two particles. Of course, whenever we use some energy, we lose energy in the process. Now, I would not go into the sustainability discussion here, and I'm not qualified for it. The video wanted to, as in I wanted to, give you a primer on the second law of thermodynamics, and importantly give you the limitations and the paradoxes it causes and the open questions in this area. Now you might be wondering, then what is the other explanation, what is the other theory that I keep talking about? The theory, I can't start it because it's been a while now. How long is it? It's been 46 minutes. I predicted 48 minutes. So I'll talk for a minute and 20 seconds. And because if I do that, your curiosity might be piqued, but then, okay, I'll just give you some things to think about. What happens when you run your life backwards? When like you were born, because like you were taken out of the ground and you were dead, and slowly you came, like you suddenly came back to life, and then you were nursed back to health in an hospital, and then you go to your house that you always had. I'm talking about an old person like coming back from dead and going to like finally the person would be a baby who would be put inside his mother who would absorb him if time ran backwards. But the question is, at any point, like at this point, if I have come from the future and I'm going into the past, would I even know? If time ran backwards, would we know? And initially you might think, yes, of course I know, what stupidity is that? But he actually shows how we wouldn't know. We would still think that we are going in the future even if we are coming from the future, because that's how memory has to be organized for the memory to make sense. So it disturbed me when I read that last chapter in this book about the mental consequences of his reversibility theory, that if time was running backwards, I wouldn't know if I'm a real living organism or I'm a pseudo living organism. The pseudo living organism thinks that it's also real, but these are again hypothetical things and it's not standard physics. But it is still interesting to think about. You know what, I'll take a minute more to explain what the reversibility theory is. Okay, so imagine I throw a ball down the stairs. What happens, it just jumps and jumps and jumps and jumps and finally comes to an end. It would be ridiculous to think that the floor suddenly, the energy suddenly came together and pushed the ball up and it jumped on the next step, and at the right time all the energy flowed in that step and then pushed the ball up again, and then it just jumped and then I grabbed it. But imagine, take a little portion of this into consideration, and that also feels wrong, because what happens when the ball suddenly hits me like this? Here you can see that I am absorbing energy and stopping, and that seems right, because when you catch a ball, you do absorb its energy and that must go into the heat of the body, etc. But then are you saying that when I throw the ball my hand gets colder? So there is something opposite in the non-living world and the living world. and he lists down a lot of phenomena that could be experienced, biological phenomena, through the through an idea that every living organism has a reverse tendency of the second law of thermodynamics. So they follow the reverse of the law until they suddenly don't, and then they follow, as like every other dead matter, the second law of thermodynamics. And then he also goes into say that there are portions of the universe where there is only the reverse law works, and it might seem ridiculous when you start hearing about these things, but when you read it, of course, when you're discussing a new physical theory, there are drawbacks and problems, etc. But there are interesting things that are just fun to think about. Why can't we be like mathematicians for once in a while? Just create abstract theories and see what interesting it would be. At worst, you have science fiction. At best, you explain the physics. No, I was going to tell you something interesting, that the consequences of he very accurately described an event horizon of a black hole in like 1920. The book was written in 1915 to 1920, and the description is so real of something that had not even been thought of. It was before general relativity. Yes, general relativity was published in 1915, but people didn't start reading it until later, especially not before 1919. So yeah, I hope you liked the video. I did. This is my longest video ever. It's like a full-on lecture. 50 minutes is how long our lectures were in college. Thank you.